So, in this particular problem, I don't think anyone's going to argue that the left-hand side looks more complicated than the right-hand side, so we'll start there. I got some simple trig functions, sines and cosines, so I can't break those down. There's no trig functions being squared, so I can't use Pythagoras' identities. So we just use arithmetic. We're adding fractions here, so to add and subtract fractions, they need to have the common denominator. I hope it doesn't take a lot of thinking to see that the common denominator is just both of these guys together. For the purpose of this video, I'll go ahead and just show the work. So the left fraction needs a 1 plus cosine. So I hope you guys can see that this was the original fraction on the left fraction, and all we did was we multiplied the top and bottom by 1 plus cosine. All right, so that's legal to do. Plus, and then this fraction needs a sine. Again, I'm just going to show my work here. So again, here is the original right fraction, sine over 1 plus cosine, and all we did was we multiplied top and bottom by sine. Right. So then, now that the denominators are the same, we go ahead and put it as one fraction. I typically do not multiply out the LCDs. Sometimes you need to, sometimes you don't, so no need to rush it. But the numerators I will multiply. So if you were to properly expand the numerator, FOIL if you will, you'll get 1 plus 2 cosine theta plus cosine squared theta plus, and then this guy here is sine squared theta. Well, hopefully we can recognize that cosine squared plus sine squared, that's Pythagorean identity, that's 1. And since we already have a 1 here, 1 plus 1 gives us 2. And then we should recognize that in the numerators, we have two 2's, right? So it's factorable. We can factor out the 2. And what do you know? The 1 plus cosines now cancels out, and that is precisely, I believe, the right-hand side. That's exactly what the proof wanted. Let me just confirm. 2 over sine theta. Yep, 2 over sine theta. So that's it. Pretty simple.